Today what we're going to look at is Chapter 5.5, Solving Absolute Value Inequalities. And the first thing we want to do is kind of see why and where we would use these absolute value inequalities. So some companies use absolute value inequalities to control the quality of their product. Okay, it's kind of like quality assurance, quality control. You want to actually know what you're making. So to make baby carrots, long carrots are sliced into 3-inch sections and peeled. If the machine is accurate to within 1/8 of an inch, the lengths range from 2 7/8 inches to 3 1/8 inches. Sometimes you'll hear this said that this machine is accurate to within 1/8 of an inch. Okay? Anytime you do measurement, there's some amount of error, and there's only so accurate you can be when you take a measurement. Either you or a machine or electronically, anything you do with a measurement, there's only so accurate you can be. And so it has to tell you what the tolerances are. That's another word that you might have heard, tolerance. And so how much are you willing to give on each side, and what will fall within that tolerance? What will fall within that plus or minus? That's where you see it a lot, plus or minus. So what we're going to do is we're going to start with the answer. Thinking back to the compound inequalities that we've done, we're going to look and say, okay, since we're starting at 3 and we're between 1/8 of 3, really we're at 2 7/8 and 3 1/8. And since those two numbers are inclusive to what we're talking about, they're going to have closed circles. Now, since we're saying this thing, these carrots, have to be within these two boundaries, okay, it has to be within 1/8 of 3, we're talking about or equal to, and that's why I would put my closed circle. And since they have to be within this, that means they have to be between these two numbers, and numbers that are between these two numbers get the bar shape that we've seen before. Okay? If I wanted to write this using my inequality symbol that we learned back in compound inequalities, I would write less than or equal to, choose a variable to represent all the numbers in between, that's now colored in by blue, okay, but not including the dots, and I would write less than or equal to. This would be my answer. But what we're really looking at is a middle number, 3, and a certain amount of distance away from that 3. How much distance? Well, 1/8 on this side, and 1/8 on this side. And so way back when, we want to think about what we did when we saw a plus or minus. We're talking about 3 plus or minus 1/8. And so way back when, we talked about something called the absolute value. And the absolute value represents the distance away from a certain number. Usually 0, but in this case, it's the distance away from 3. And so we're going to use that in our answer. We're going to use that knowledge, that concept, to write our answers. Notice, though, if you start back with compound inequalities, the answers to an absolute value inequality problem will look like the answer to a compound inequality problem. Okay? So the first thing we're going to start with, how can you use this? And now we're going to look at a word problem where this actually is used. So, as you can see the boat on the left, sometimes sailors use a laser range finder. So a laser range finder is literally a laser that is shot at something that's solid or shot towards something. And lasers move at a certain speed. We can figure out the distance. And so if we know distance and time, we can actually find how far away we are, right? We did this way back when that distance is equal to rate times time. Well, if I know how fast it's going, the laser, speed of light, which is constant, and I know the amount of time it takes to go from where you're firing the laser to the thing you're pointing at and for it to come back, I can multiply these two numbers and find the distance. But again, with every kind of measurement that you make, even though it's using light, using lasers, and there's an accuracy issue. Okay, and it's not an issue, it's just a fact of life. Every time you measure something, there is an amount of accuracy. There's only a certain amount of accuracy that you can get. So what we're going to do is figure out, hey, how does this apply to absolute value? So they use a laser range finder to determine distances. Suppose one such range finder is accurate to plus or minus 0.5 of a yard. Okay, that means that if the sailor estimating the distance to shore reads 323.1 yards on the laser finder, that means plus 0.5 to that number and minus 0.5 to that number. So what that means is the distance to shore might actually be as close as 322.6 or as far as 323.6. So it's both within 0.5 of the actual reading. And there's no way we can get around that. Every type of measurement that we do has some sort of error in it. But one thing we want to look at is this. When you're talking about only the maximum distance and the minimum distance, I'm going to refer you back to absolute value equations, which we did. And what we really want to do is we want to look at the fact that we have a certain distance. So we're going to say E is what we're talking about. And that E is going to be equal to the number that we actually read on the laser finder plus or minus 0.5. And remember to think back how we did this. In order to write this as an absolute value, remember that the absolute value is the distance away from something. Well, what's the distance away from the reading that we have? The distance away is 0.5. And so what we're going to do is we're going to subtract 323.1 from both sides and end up with E minus 323.1 is equal to plus or minus 0.5. And if you remember how we interpreted that, we said, okay, the difference, because the distance, we're actually measuring the difference. If we have plus or minus that number stays where it was. And on the other side, we convert what we were looking at, 323.1, into the absolute value. Because the absolute value is the distance away from this number. And so we're looking at 323.1 as the middle, and the absolute value is going to be equal to plus or minus that number. And that's why the equal sign is here. So that's how this equation came about. Okay? That's where that equation comes from, just to remind you what we did for absolute value equations. Okay? So now, since we know where that equation came about from, we know what we would do if we had maximum or minimum, if that's the only thing we were looking for. But if I want to find all the range of numbers for which can actually apply to this, I'm still going to have an absolute value. It's still going to look the same way. I'm still going to put it together the same way. But what I'm going to be looking at is an inequality. Whereas the one with the equal sign only gives me a maximum number, this one, or a minimum number, this one. The inequality, this inequality symbol, what it does is it allows me to talk about all the numbers in between the minimum and the maximum, including both. And that's why it's less than or equal to. The difference between what number you read and the actual number has to be less than or equal to 0.5. So this is how we would look at a word problem for these types of problems. Now, what we're going to do is we're going to look at how we actually solve something like this. Very similar to the way that we solve it for solving an absolute value equation, but now we're going to have to add in the portion that is the less than or greater than, because there's still the or equal to portion here. So, reminder for absolute value equations, how we solve them. First, you want to isolate the absolute value sign like it was a variable. You want to separate into the original case or the opposite case. And what does that mean? That's case 1 and case 2. The original looks just like the problem. The opposite case looks like the problem with a minus sign. You want to solve each case and check your answer so that you know what's going on. So this is an example we're going to use. And this is a fairly complex one to start with, but I believe that we can do it. So we're going to treat the absolute value like it's a variable. We're going to do everything we need to do to isolate it. And now we have the absolute value isolated is equal to 14. From that, what we're going to do is split it up. There's two cases to this. There's the one on the left, which I would call the original case. And I call it the original because it's basically just what exactly you're looking at for the absolute value with a positive distance, or in the positive direction, plus 14 of what we're talking about. And then on the other side, this is the opposite case. And this opposite case is saying we still have what we're talking about, but we're actually going in the negative direction. Remember, distance is basically going to be positive. That's why the absolute value is equal to a positive number. But the absolute value really represents two types of things, going in the positive direction or the negative direction. Okay? So, just like all absolute value equations, we're going to solve both parts of this. So we solve both parts by adding eighth to both sides, because it's the additive inverse, and we get x equals to 22, and x is equal to -6. And so now that we have both of those, we could check them, plug it in, and when you plug it in and check, it checks. So this is just a quick reminder of absolute value equations, how we do them, how we did them, and now we're going to use this same process to solve an absolute value inequality. So starting with this one, we're going to look at absolute value of 3p minus 12 is less than 9. So again, I'm going to split it up into my original on this side and my opposite. Okay, if you like it to switch it to the other side where you want the one that's kind of going in the negative direction to be on this side, you do the opposite and the original. Doesn't really matter, as long as you remember that you still have to do two cases. So if this is my opposite, I have 3p minus 12, and since I'm splitting it up, I'm going to put -9 over here, and I'm going to come back to that. I have 3p minus 12 on the right, and I'm going to put less than positive 9. So my original pretty much looks like what I have with my absolute value without the absolute value. But we now have to look at what happens when I take this. That minus sign is just like taking the original case, the 9, and multiplying it by a negative. And what we learned earlier in this chapter is that when we multiply an inequality by a negative, what we're doing is we're flipping the inequality sign. And so to keep the inequality true and to justify what we're doing, because remember we're looking at the opposite case, since we're putting in the -9, we have to now not have our inequality sign be open to the right. We now have to have it be open to the left. And now I've kept the truth value of this because I flipped my inequality sign because I changed the sign of the opposite case. I kept it the same for the original case. Notice what I'm changing. I'm not changing what's in the absolute value. I'm changing what's on the other side. And now I can actually solve both of these just like I would solve any other absolute value that we've done. This is a two-step absolute value. And so I'm going to solve by doing additive inverses first. Then I get 3p is greater than 3. I'm going to divide both sides by 3. And I get p is greater than 1. On the left, again, additive inverse. I get 3p is less than 21. Divide by 3. And I'm going to get p is less than 7. As with any other inequality where you get two sets of answers, it's going to look like, when you graph it, a compound inequality. So I think graphing it is usually easier than writing the answer in set notation first, so I'm going to graph it. And again, I take my boundary numbers. 1 is less than 7, so 1 goes on the left, 7 goes on the right. And then I'm going to read exactly what this is saying to me. Well, I don't have an or equal to for either one of these, so these are both like electric fences. I can get close, but I can't touch it. So I have open circles for both of them. On the left, it says p is greater than 1. Well, greater than 1 goes to the right, so I'm starting at 1 and going that way. On the right-hand side, it says p is less than 7. Less than goes this way. And so now I notice that these two electric fences are keeping the numbers we're talking about on the inside, and therefore this is an AND statement, because the p value goes where the bar is, and so this is an AND statement. This is a statement saying this has to be true for both things. So now when I write it in set builder notation, p such that it's a little bit easier for me to write this. I know that 1 is one of the numbers. I know that 7 is the other. I know my variable has to end up on the inside, and I know that 1 is less than p, and I know that p is less than 7, and with my fancy brackets. So I've graphed it, and I have written it in set builder notation for my answer. Okay, I could go back up and check it if I really needed to, and then if I check it, I plug in 1 in here, and I have 3 times 1 minus 12 is, in the absolute value, is less than 9. And so 3 times 1 is 3, minus 12 is minus 9, but it's in the absolute value, so when it comes out, it becomes positive 9, because remember, absolute value is the distance from. So really, minus 9 is 9 away from 0. And so, as we want to make sure we're clear, is 9 less than 9? Are we going to end up with a correct statement? No. And why did I end up with something that's wrong here? Well, if you look at our inequality sign, our inequality is saying that all the numbers I can pick have to be in between 1 and 7, not 1 and 7. So this should be false. Okay? So we notice that any number that's 1 or less than 1 doesn't make this true. If I check a different number, for example, if I check what's between 1 and 7, if I check 5 or 6, it doesn't matter. If I check 5, I get 3 times 5 minus 12. Absolute value is less than 9, because I always want to check in the original. I get 15 minus 12 less than 9. 15 minus 12 is 3. I get positive 3 in here. The distance that positive 3 is from 0 is 3, so 3 is less than 9. That is true. I picked a number in between, and look, I got the correct answer. I picked a number that was a boundary that was not included in my answer because of the open circle. I ended up with a false statement. The next one we're going to look at is this one, and we're going to try to do exactly the same type of thing. But before we just jump into the problem, we want to read it and think about what it says for a second. This problem is saying that the absolute value of x plus 5 is less than 10. Now, going back to what the absolute value represents, it represents the distance away from something. So the distance that we always talk about, if we remember, always has to be positive. Because when I end up finishing an absolute value problem, if I plug something in there and pull it out, it becomes positive. Okay? Just for reference, look back over here. I had minus 9. When I pulled it out of the absolute value, the distance was positive. Well, you should see something wrong with this. Is it possible to get a positive number that's less than a negative number? Well, the answer to that is no. And because that's not possible, can't get a negative, it's not possible, you have to actually say there's no solution. There's an empty set. Okay? The set of all answers that we can find, the group of answers that we can find doesn't exist. And so this is no solution. Because it doesn't make sense that you can have a positive number less than a negative number. This problem, we're using the inequality sign going in the other direction. This is a greater than, so the absolute value is actually greater than the number 4. Again, split it up into 2. Okay? So I'm going to do the original on this side this time, and the opposite on the other side. Why? Because it doesn't matter. You just remember that you're doing 2 of them. So I have x minus 7 is greater than 4, and I have x minus 7 is now, put my opposite, and since it says x minus 7 on the original over here is greater than 4, for my opposite, it has to be opposite of greater than 4, which would be less than negative 4. Because I'm flipping the inequality sign since I'm making what it's less than or equal to negative. Okay? Notice when I just start out the problem, there's nothing wrong with the problem, right? I have a positive absolute value is greater than a positive number. That actually works, okay, regardless of what we're looking at. So when I do each side, if I add 7 to both sides because the additive inverse, I get x is greater than 11. And if I add 7 to both sides because the additive inverse, I get x is less than 3. Okay, make sure you saw how that happened. So now I have these 2 inequalities, and now I like to graph it first because that usually helps me write my solution set. And so, as always, boundary numbers, 11, 3. This one says that x is greater than 11. Well, since it's first, I'm going to put down my circles. So 11, we have an open circle, electric fence. For x is less than 3, open circle, another electric fence. On the left, for the original, it says x is greater than 11. Greater than numbers go to the right. For the other one, for the opposite, it says x is less than 3. Less than numbers go to the left. This, clearly now, since it's two separate pieces, but it's a compound inequality using two simple statements, is clearly an OR problem. And so, when I write my set builder notation inequality for my solution set, I get the variable that I had, x, is such that x is what? Well, this x would be less than 3, or this x on the right would be x greater than 11. Okay, you could also write 11 less than x. If that makes you feel happier, I'm okay with it. Okay? So now we're going to look at another one of these problems, and you think, okay, there's a little gray box there, so there might be another trick to it, but we really want to pay attention when we start the problem to, is this problem even accessible for us to do? So when we look at this, it says the absolute value is greater than or equal to a negative number. Well, since it's an isolated absolute value, and it's greater than or equal to a negative number, lo and behold, it's always going to be true. Why? Because if this always has to be positive, there's never a time when a positive number can be less than a negative number. Therefore, all of the time when you look at something, a positive number will always be greater than or equal to a negative number. Always. So therefore, instead of no solution, which could never be true, we have all real numbers, which is always true. And so, when you write your set builder notation, you write it like this. You write it with all real numbers. And you want to realize why this is happening, right? Since the absolute value is always greater than or equal to 0, that means it's always greater than or equal to a negative number. Therefore, all of the answers you plug into that inequality will always be true. Doesn't matter what you pick, any number you like. If you like decimals, if you like fractions, if you like negatives, positives, or 0, always will work in that inequality. And so, if I wanted to graph this, it actually just turns out the graph of this is the entire line. Doesn't matter which number you pick, so it's the whole line. Now we want to look at a word problem, so now we're going to put it all together. So first we practiced how we solve our inequalities, our absolute value inequalities, and we also looked at how you write an absolute value inequality based on the word problem. And since this is talking about the range of numbers, this is the clue, or the range of depths, excuse me. All right? The range of depths that we can talk about, since it's the range, that means we're not just talking about the maximum and the minimum, we're talking about all of the numbers, inclusive, between. Okay? So using that to our own knowledge, what we're going to do is read through and figure out what's going on. So the average depth is 4 feet. When rainfall or evaporation, so rainfall is going to make the river go higher, more depth. The evaporation is going to make the river go lower, less depth. The depth of the river is within 0.25 feet of the average. So within, so if we have 4, it's going to be plus or minus 0.25 of whatever the average depth is. So I'm going to write my let statement, because that's how we do word problems. Let D equal, okay, the depth of the river. That's what D is equal to. So I'm going to use the letter D, and that D is equal to the depth of the river. And so, since we're talking about the range of depths, we're not going to use the equal sign for the max and the min. We're going to use the range of numbers. And so the range of numbers for this has to fall below, less than or equal to, 4 feet plus or minus this. Okay? That's what we're really talking about. Because remember, it's within. This word is very important. It's within. The depth that we're talking about has to be within, which means it has to be equal to or less than. Okay? The or equal to part means it's inclusive, and the less than part means the depth of the river has to be less than the maximum, but greater than the minimum. It's within those two boundaries. It's not outside those two boundaries. So, just like any other inequality, just like we did with the absolute value equations, we have D is less than or equal to 4 plus or minus 0.25. I move the 4 to the other side by doing the additive inverse. And I get D is minus 4 less than or equal to plus or minus 0.25. And then remember what happens to our plus or minus when we use the absolute value. This doesn't magically go away. We use the definition of the absolute value to remove the plus or minus. And you go d is d minus 4 absolute value. The thing we're talking about must be within 0.25 of what we're talking about. If it was saying it has to be bigger than or less than, has to be outside those bounds, it would be facing towards the absolute value. But this one is saying it has to be within that boundary. So now that we've done that, we have an absolute value that we can use for this. And so if you're writing the when you write the absolute value inequality that goes with a problem like this is how you would write it. Now, to find the answer, we didn't have to go that far. Okay? We didn't have to go that far specifically because they're asking you what is the range. Well, the range should be 4 plus 0.25. That's the highest. That's the max. That's right. And then the minimum should be 4 minus 0.25. Okay, which would be 3.75. So based on what we have written here, I know what my answers are going to end up being. It's going to be between 3.75 and 4.25. To show my algebra so that I can show you and prove to you how I did that, we'll do exactly what I've done before. Split it up. Okay, d minus 4 is less than or equal to 0.25. That's the original. I'm going to do the opposite. D minus 4 is greater than or equal to, because I must flip my inequality, to minus 0.25. Solve for what I have, and I'm going to end up with d is greater than or equal to 3.75, which we already know that's what it should be, because that's the minimum. And d on this side is going to be less than or equal to 4.25, and we already know that because that's going to be the maximum. So this is a good way to check yourself to see what's happening. If I wanted to graph this, I would do the following. Number line, okay, I would have 3.75, because that's lower, that's the smaller one down here. Closed circle, that's one boundary. I would have 4.25 up here, that's another boundary. And since this has to fall within that range, that's what it's talking about. Another way to see it is this over here on the left says d must be less than 4.25, which is going this way. And this over here says d must be greater than 3.75, which is going that way. So we see that this is an AND problem. Again, the variable that I define all the way back up in the beginning, okay, all the way back up in the beginning is d. And so in my set builder notation, I would write d such that 3.75 is less than or equal to d less than or equal to 4.25. Fancy bracket. Writing this out in words to really say what the meaning is, in words, I'm actually going to say the depths of, or the depth, without the S, of the river can be 3.75, and what were they talking about? Feet, I think it was? Feet, 3.75 feet to 4.25 feet. And I've written out exactly what we're talking about. I've defined what the variable means in my let statement. I showed what the max and the min could be. I talked about what my inequality looks like, and I use my inequality to solve within set builder notation and in words. If you haven't kind of picked up on this, okay, this is just kind of a quick, just look at it guide, and you want to kind of have this in the back of your mind, but you definitely want to make sure you can show your work and say how you got all your steps. But when we're talking about less than or equal to, okay, we're really talking about when the absolute value we're talking about is going to be within something. Okay, so if it's within, inclusive, trapped between, okay, within some number. So if I go all the way back to the beginning, the point 0.5, and these are closed circles, so it's less than or equal to. But if it was just less than, it would be the absolute value is less than some number. That usually means it's inclusive. It's going to look like this. Okay, if we look at the absolute value is greater than or equal to, it's going to be outside these two numbers. And that means the absolute value is going to be greater than some amount. It has to be outside this range. So pretend the number was 5. If it's greater than, the absolute value is saying all the distances I'm talking about have to be outside of 5. Okay, outside of that range. So just a quick once over of, oh, this problem is talking about less than or equal to, or greater than or equal to. This is probably what I should end up. Just kind of some math background. Thank you guys, and I'll see you guys tomorrow.